Hey guys, so today we're going to be covering a concept called mass points. Mass points is a really useful tool in a lot of geometry problems. It's not taught in a lot of schools, so I thought it would be useful to teach it to you guys today. So let's just take a look at what kinds of problems mass points are used in. So if you look at this top diagram here, we have triangle ABC, and we have these lines that are called Chevians. Chevians basically are line segments that extend from one vertice of the triangle to a point on the opposite side. So for example, BE, CF, and AD are the Chevians in this example. And basically, mass points help us get a lot of information concerning just the ratios between all of these line segments. So for example, we can use mass points to figure out the ratio between CG to GF or BD to DC, given just a little information. So let's just start with the basic example. Mass points are based on physics, and it uses the idea that any system of points has a center of mass. So let's look at the example where we have 2 points. We have A and B here, and their center of mass is going to be C. So let's say we have a ball A on the left side here, and let's say it has a weight of 2, and the smaller ball B has a weight of 1. Intuitively, we're going to have to place this ball A closer to the fulcrum C, and then ball B farther away so that the seesaw is balanced, because this ball A is heavier than ball B. And it turns out that the distance we place it away from the fulcrum actually matters. So the product of the distance times the weight must be equal for the seesaw to be balanced. So this means that we can place this distance of 1 away from the fulcrum, and then ball B a distance of 2, because 2 times 1 is 2. And this system will be balanced in this case. It gets a lot more interesting when we consider the case where we have more than 2 points, which is what you can see in the bottom here. So essentially, when we're considering a triangle, we use the idea that, well, there's a really powerful concept in mass points, which is the concept of associativity, which is basically says that the center of mass of, well, I'll just write it down. Let's say we have the center of mass of 3 points A, B, and C. I'll just use a plus sign to make it clearer. So this would be the center of mass of the 3 points A, B, and C. What associativity tells us is that we can take any 2 points and find the center of mass of those two first, and it will still give us the same center of mass as if we were to deal with them all together. So this means that in this triangle here, the center of mass of A plus B will be F, and then the center of mass of C and F will be G, and that's going to be the center of mass of the entire triangle, which is point G here. So let's just see how we can solve this problem using mass points. We're given the information that AG to GD is in a ratio of 3 to 2, and the ratio of BD to DC is 1 to 1, so they're equal. So let's assign some masses. AG to GD is 3 to 2, so the length of AG, let's say, is 3, and the length of GD is 2. And the reason we can do this is because we're finding ratios. We're trying to find CG to GF, so if we assign, this could be like 6 to 4, 9 to 6, and it wouldn't matter because we're finding the ratios, and it's going to stay constant. Okay, So AG to GD is 3 to 2. So if we were to assign masses to these points A and D, well, D would have to have a mass of 3, and A would have to have a mass of 2. Because 3 times 2 is 6, 2 times 3 is 6. Now let's use this information here. BD to DC is 1 to 1. What does this mean? Well, this means that B and C, they must have an equal mass. Because this distance here is, it says x and x. And the center of mass is going to be the sum. The mass of at the center is going to be the sum of each part. So we know that B and C have equal masses, so each one has a weight of 1.5, or mass of 1.5. And we can do that. We can find the sums of E and F. So E is going to have 2 plus 1.5 is 3.5, and similarly F is going to also be 2 plus 1.5 is 3.5. And we want to find CG to GF. We have the weights here, which are going to be 1.5 to 3.5. So this means that the ratio CG to GF must be 3.5 to 1.5. Because if you look at the products, we have 3.5y here and 1.5y. This seesaw will be balanced if you just look at the products. And then if you take the ratio, the y's cancel out, and you're left with 3.5 to 1.5. So that's just the first problem. I've also prepared a problem from the AMC 8 that we can also look at. This is going to be the 2019 AMC 8, number 24. In triangle ABC, point D divides side AC so that AD to DC is 1 to 2. So let's just write x to 2x. Let E be the midpoint of BD. So these are equal. I'll just say y to y. And let F be the point of intersection of line BC and line AE. Given that the area of triangle ABC is 360, what is the area of EBF? Okay, so let's just figure out a strategy. We want to find the area of triangle EBF. Well, we can compare the area of EBF to the area of ABF if we find the ratio of EF to AF. And we can also find the area of ABF by comparing it to ABC, by finding the ratio of BF to BC. So that's how I want to solve this problem. So we know that AD to DC is 1 to 2. So let's just use our mass points again. A must have a mass of 2. C must have a mass of 1. Because 2 times x is 2x, 1 times 2x is 2x. And because that's 2 and 1, D must have a mass of 3. Because 2 plus 1 is 3. We know that BE is equal to DE because E is a midpoint. So B must have a mass of 3. And so this point E will have a mass of 3 plus 3, which is 6. And then we have this center of mass here, AF. We know that the mass of A plus the mass of F must have a mass of 6. So F has a mass of 6. Sorry, 4. And if you notice, this entire system is balanced because 3 plus 1 is also 4. Okay. So we know that the area of ABC is 360. And, okay, so this entire triangle is 360. First, we want to find the area of ABF. Well, we know that the ratio of BF to CF is 1 to 3. Because this has a mass of 3 and this has a mass of 1. I'll just erase these because they don't really matter anymore. So this means that this length here is 1/4 of this entire part, because this is x and this entire length is x plus 3x, which is 4x. So this triangle ABF has an area of 1/4 times 360, which is 90. And the reason we can just take the ratio of the bases is because they have an equal height. And if you just look at the area formula, which is just 1/2 base times height, 1/2 each is going to be equal, so you're just left with the ratio of the bases. Okay, now that we know the area of ABF, which is 90, we want to find the area of EBF. We know that the ratio of EF to AE is 1 to 2, because that's the same as just 2 to 4, which is 1 to 2. So we can just say that EF to AE is 1/2. And we know that, okay, so let's just say this is Z and this is 2Z. We want to find the ratio of EF to this entire length, AF, because we know the area of ABF, which is 90, and we know that triangle EBF shares a height with triangle ABF. So finding the ratio of the bases will also give us the area of EBF. And so FE to EA is a ratio of 1 to 2. So the ratio of FE to the entire base, FA, is going to be Z divided by Z plus 2Z, which is 3Z. So Z divided by 3Z is 1/3. So the area of EBF is going to be 1/3 the area of ABF. So that's going to be 1/3 times 90, which is equal to 30. That's going to be our answer, which is B. So that's just kind of an idea of how we use mass points to figure out the ratios of lengths in a triangle. Essentially, you use the given information. In this case, we had like these side length ratios. And then using that information, you assign weights and balance the entire system. And then you use the weights to figure out the ratios of the corresponding sides that you want to figure out. So that's a broad overview of how mass points works. If you enjoyed the video, be sure to like, comment, and subscribe, and I'll see you in the next video.